Ladies and gentlemen, if I asked you, what are the 6 shapes in front of you? You would say they are triangles. Are they the same triangles or different triangles? You would tell me, well, they're different triangles, of course, because each triangle has colors on different sides of the triangle. And I would say, yes, absolutely, you're right. These are 6 different triangles. But what if I asked you, what are these triangles after I've removed all of these colors? You would tell me, now they're the same triangles. They're in fact exactly the same except for the colors on the edges. Well, that is the subject of today's lesson. Lesson 4 in our group theory course talks about the dihedral group mostly. But also we'll be talking about something that you've been taking since 3rd grade, and that is the multiplication tables. The first thing you've done when you were talking about numbers and multiplication is putting them together in a table and seeing all the different possible outcomes. Well, that is exactly what we're going to be doing, but for groups. And then I'll give you a little bit of examples for these multiplication tables, and then we will see if there is a very nice connection between some of these groups. Afterwards, we'll be talking about the dihedral group, D to N, and lastly, we'll be mentioning what generators and relations do and how they simplify our lives in describing groups. And we will use the dihedral group as an example. Our first order of business is talking about multiplication tables. Let G be some finite group, G1 till Gn, G1 being the identity element. Then a multiplication table of G is given by this table that you see in front of you right here. So what do we get if we do G1 times G1? Well, we simply get this product. But we can also say that is equivalent to saying G1, G1. This is notation we've previously discussed. But we can also say, because they're repeated, we can say it's G1 squared. So these are 3 ways I've just explained to you how to describe the same thing. What about G1 times G2? Well, that's just G1, G2. And lastly, G1, Gn is the product, G1, Gn. G2, G1 is G2, G1. G2, G2 is G2 squared. And lastly, G2, Gn. And in the last row, we just fill out the table the same way. We get Gn, G1, Gn, G2, Gn, Gn. And that, the table, gives you all the possible outcomes of the products of the elements in the group G. We will now consider some examples on the multiplication tables. Consider 2 groups, Z for Z with operation addition, and Z and Z with operation multiplication. For Z, we have all the numbers between 0 and 3. And for Z 10 Z star, we have all the elements that are co-prime to 10. So it's 1, 3, 7, and 9. For the first multiplication table, we will add the elements together to fill it out. So we have 0 plus 0 is 0, 0 plus 1 is 1, and so on and so forth. And because addition is commutative, which means that it does not matter the order in which we add the elements, we can have the same results on the first row as in the first column. So it would give me 0, 1, 2, and 3. So in a way, multiplication tables are symmetric about this axis here if the operation is commutative, which is good news. It saves me a lot of time and a lot of effort. So what about 1 added to any element? What would that give me? So 1 plus 0 is already 1, we know that. 1 plus 1 is 2, 1 plus 2 is 3, and 1 plus 3 is 4, but 4 is not on the list. What do we do then? Well, we can reduce it modulo 4. So when we divide 4 by 4, we get a remainder of 0. We're interested in the remainder after division by 4. We do the same thing with 2. So 2 plus 1 gives me 3. 2 plus 2 gives me 4, which again is 0. 2 plus 3 is 5. And 5 divided by 4 gives me a remainder of 1. 3, the same thing with 3. 3 plus 1 is 4, which is 0. 3 plus 2 is 5, which is 1. 3 plus 3 is 6, which is 2. For multiplication, z times z, we just multiply the elements together and see what we get when we reduce it modulo 10. So 1 times 1 is 1, 1 times 3 is 3, 9, and 7, because 1 is the identity element, it changes nothing about the other elements. Since multiplication is commutative, the table there is already symmetric. So we just say 3, 9, and 7. About 3, we say 3 times 3 is 9. 3 times 9 is 27, which is 7, because 7 is the remainder when dividing 27 by 10. And 3 times 7 is 21. 9 times 3 is 27. 9 times 9 is 81. And 9 times 7 is 63. We can make use of commutativity by putting 1 here, and we putting 3 here, and by putting 9 over here. I have already filled all of the last row without even needing to calculate the elements. And why is that? Because I made use of the symmetry of the table. I made use that the table is symmetric about this axis. So I know that whatever is written here is exactly equal to whatever is written here. Whatever is written here, it's exactly equal to whatever is written there. And the element here is the only element left that I have not written in the list. Now, you will tell me, is there a reason you have put these two tables next to each other? And I will tell you, yes, there is a very important reason why Z4Z and Z10Z star are actually very related. They are in fact the same group. And you will ask me, why is that? I will tell you, well, it's true that the operations are different. It's true that the labeling of the elements are different, but they both have 4 elements. They both have an identity element, and if we can show that the elements interact with each other the same way, then maybe we can say that these groups have the same structure. And then we would stop caring about what labeling we give our elements. We could label them 0, 1, 2, 3, 1, 3, 7, 9, apples, oranges, peas, and strawberries, but we don't really care about the labeling. All we care about is the structure of our group. And if I pose the following correspondence, let's pose the correspondence for each of the elements in Z4Z. I will correspond it to a specific element in Z10Z. So for 0, I will correspond the element 1, which makes sense, right? Because 0 and 1 are both the identity elements of their respective groups. For 1, I will give 3. For 2, I will not give 7, I will give 9. And for 3, I will give the element 7. So after doing these correspondences between the elements, I will be testing them out. I will see if the elements interact with each other the same way. What do I mean by that? Well, let's take an example. Let's take the element 1 bar and 2 bar from Z4Z, and let's add them together. The multiplication tells us that, the multiplication table tells us that 1 plus 2 is 3. Okay, let's replace 1, 2, and 3 by the replacements that I've set there. So 1 is replaced by 3, 2 is replaced by 9, and 3 is replaced by 7. And the plus is replaced by the multiplication. And in fact, the second equation is true, the same way the first equation is true. So that means that the elements interact with themselves the same way. So the same way that 1 plus 2 gives us 3, 3 and 9 gives us 7. And in fact, if you try that out with any of the operations, any of the elements in the group, you will get the same result. This means that the two groups have the same structure and are in fact isomorphic. What we call an isomorphism, we will describe later in future videos. I don't like this. Now you would ask me if there is a specific reason that I've put these two groups next to each other. And I would tell you, there is in fact a very important reason I did that. In fact, even though Z4Z and Z10Z star have a different operation, they have different set of elements, because they have very similar structure, in fact the same structure, they are considered to be isomorphic. Isomorphism means that they have the same structure, and in fact they can be considered, for all intents and purposes, the same group. And I will tell you why is that. It's because if we replace the operation plus with multiplication, and if we replace each of the elements in Z4Z by one of the elements in Z10Z star, we will have a very similar interaction between the elements. And I will show you exactly how that works out. So let us see the correspondence between Z4Z and Z10Z. We will correspond each of the elements in Z4Z with a single element in Z10Z. We will correspond the element 0 with 1, which makes sense because 0 is the identity element of Z4Z and 1 is the identity element of Z10Z. And the element 1 we will correspond to 3 in Z10Z. The element 2 we will correspond to not 7, 9. You ask me why, I tell you no reason. I just pose these correspondences and then I test if they work out or not. So 3 will be corresponded to 7. So there is a one-to-one bijection between these four elements and these four elements. Let us test them out. I'll give you an example, but you can test the other ones on your own time. Let's see. So let's take the elements 1 and 2 from Z4Z and let's add them. What we get is 1 plus 2 gives us 3. Z10Z, we will take the corresponding elements and we will multiply them because we are in Z10Z. So 3 and 9 gives us 27, which is 7. And that is in fact the product that we were looking for. So 1 plus 2 gives us 3, and 3 times 9 gives us 7. So even though we have shifted from the first four elements to the second four elements, the interactions between the elements did not change. The way they were interacting is the same. They have the same structure. You can try that out with other examples. Try it with 2 times 3, try with 2 plus 3, 2 plus 1, 3 plus 1, 3 plus 0. You can try it with any of the elements. They will give you the exact same responses either way. So, this type of phenomena, where you can replace the labeling of the elements, you can replace the labeling of the operation, but you will get back the same type of structure, is called an isomorphism of groups. It means that the two groups are, for all intents and purposes, the same group. This is a very important topic that will help us in classifying the groups that there are. It will help us that we reduce the number of groups that exist in a very significant way. Our next topic of discussion follows the dihedral group D to N. The dihedral group considers all of the symmetries of a regular n-sided polygon. But what is a symmetry of a regular-sided n polygon, you would ask? And I would tell you, it is a movement of the polygon such that the shape of the polygon before and after the symmetry would remain the same. For example, what is considered a symmetry of the triangle that you see before you? Well, a symmetry, as you would see, could be considered, for example, a rotation of 60 degrees, giving you the same shaped triangle, just that it's rotated 60 degrees. Or you could tell me I would put an axis of reflection here, and then I would reflect the triangle about that axis, giving me a shape like this. That is considered a symmetry. So you can see that we don't really have that many symmetries. We could count them all by hand. And in fact, that's what we're going to do. We're going to count all of the symmetries possible, and then we're going to say this is a group. A group with the operation being if you compose two symmetries together. That is, if you perform one symmetry and then you perform another symmetry after, you would get a third symmetry. So let's see an example here. So we have a square, and in a square, n is 4 because the square has 4 sides. A symmetry here would see that the square can be rotated 90 degrees. Here I've drawn the angles, different colors, so it's clear how the square looks like exactly. The second symmetry involves rotating the square about this axis. So this axis here is important. We fix our axis and then we rotate about this axis. The third symmetry is very peculiar. You would tell me, well, we have done nothing here. And I tell you that is in fact another symmetry. It is called the do-nothing symmetry. And you would later see that this symmetry is the identity of our group. For an n-sided polygon, we have two types of symmetries in total. Either we can rotate the polygon, or we can do a reflection about a certain axis. Now the rotation, we need to quantify how many degrees we can rotate it. Well, in a circle, we have an angle of 2 pi. And the rotation depends on how many sides or how many vertices are on the polygon. So if we have 3 vertices, let's say a triangle, then each rotation would have to be 2 pi divided by 3, which is 60 degrees. So in an n-sided polygon, to be more general, we can replace the 3 by n. So that constitutes a single rotation. But what if we perform 2 rotations? Well, then it would be 2 pi over n times 2. We can do it a third time to make it times 3. We can do it a fourth time and a fifth time. We can make it a negative 1 time to go in the opposite direction. So in fact, we can say a rotation of 2 pi over n times k. So k can be from 0 all the way to n minus 1. Because if we just say k is equal to n and then n plus 1 and then n plus 2, it would be just going in repetitions. It would give us the same kind of symmetry that we had earlier. So k can be 0, 1, all the way to n minus 1. These are all the rotations that are possible. Let us consider now the reflections. We fix our axis, so we can have either this axis, we can have this axis, we can have that axis. So we fix our axis, and then we perform our reflection on that axis. I would tell you something here, very important. When you fix your axis, you don't have to change the axis anymore. By fixing the axis, you would have determined a reflection, and with that reflection, you don't need to determine any other reflection because all the other reflections are in fact going to be some symmetry you've already counted before. So you only need to fix a single axis and you count your reflections on that. So if we fix the axis in this way, we will count our reflection to have this side here go over this side here, and that side here go back to the above side. So these are in fact, these are in fact all the reflections there is. Because if you do a reflection twice, you go back to the place you started. So it is equivalent to doing nothing. Now we will move on to the notation. To notate the rotations or reflections, I will use R for rotation of 2 pi over n. That means a rotation of a single unit. R to the k means R times R times R, k times, which is just rotation of 2 pi over n times k times. So what R does is that it moves the kth vertex and it moves it to the k plus 1 vertex. So it shifts each of vertex by 1 to the right. So we say that R of k gives k plus 1. What about S? S is a reflection on a fixed axis passing through the vertex 1. So 1 is a convention that we choose. You could choose any other vertex, but I prefer choosing the vertex 1 because the vertex 1 is found in all of the polygons that we have. If we choose, for example, a vertex 4 is not really found in a triangle because a triangle only has 0, 1, and 2. So vertex, if we draw, for example, a hexagon, a vertex 1 would be here and 0, 2, 3, 4, 5. So it passes through the vertex 1 and the origin. It would look something like this. And all the reflections would be about this axis. And S of k would be n minus k plus 2. I will explain why I put n minus k plus 2. The first reason is that n minus k is a reflection, what it looks like. I will show you. Let's say that we have a triangle 0, 1, 2, right? And let's say the reflection was about the vertex 0, not 1. Okay, what happens if we replace 1 by n? Well, 2 would, if we replace 1 by k. Well, 2 in this case would be n minus k because n is 3, right? 3 minus 1 is 2. n minus k. In fact, the n minus k gives you all of the symmetrical vertices about this axis going on 0. So the n minus k takes care of the flipping. But we don't only have a flipping, we have a flipping about the vertex 1, not the vertex 0. So the plus 2 here takes care of the shifting after the flipping. The plus 2 takes care of the shifting twice because of the shifting from above and the shifting from below. And therefore, we have n minus k plus 2. Let us discuss now a very important proposition about dihedral groups. We have 6 parts in this proposition. And in each part, I will explain to you what the proposition is, what it signifies, and how to prove it. The first one says, if I is between 1 and n minus 1, then r to the ith power is never the identity, and r to the nth power is equal to the identity. This means that if I is 1 to n minus 1. So the rotation to the first power all the way to the rotation to the n minus 1th power can never equal the action of doing nothing, the symmetry of doing nothing on the polygon. This makes sense because if you rotate a triangle once, you will not get it back to where it was. If you rotate a triangle twice, neither. But if you rotate a triangle 3 times, you will get back the identity. So it has to be n, and not any number less than n. Between 1 and n minus 1, that does not work. The second part of the proposition says that s is not equal to the identity, but s squared is. In particular, the order of s is 2. The order being the smallest integer such that s to that power gives us back the identity. So s is never the identity because when you flip, s is flipping, so when you flip a polygon, you will never get it back to where it was. You have to flip it again to get it back the way it was, which is s squared is equal to 1. So that is the second part of the proposition. Okay, the third part of the proposition claims that if you do a reflection s, it will never be equal to any rotation r or its multiple, which makes sense because if you're standing in a mirror, in front of a mirror, let's say, and you wave your hand, if you rotate your hand, your thumb is still gonna be on the left side. But however, if you reflect it on the mirror, your thumb is gonna be on the right side. So no matter how many times you rotate it, your thumb and the thumb in the mirror are never gonna be on the same direction. So just think about it like that. And number 4, in the proposition, it says that SRI is not equal to SRJ if I and j are not equal, but also that I and j both have to be between 0 and n minus 1. Because if you have a 0 rotation, which is doing nothing, and maybe you have an n rotation, so then 0 and n give you the same result because it's like you rotated all the way and then you got back to where you were. So I and j have to be between 0 and n minus 1, and then and only then we will have this inequality. For number 5, it says that Rs is equal to Sr minus 1. So first of all, it's important to note that when you do Rs, you apply S first, and then you apply R. So you apply a reflection, and then you apply a rotation. And on the right-hand side of the equation, you apply R to the minus 1, which is a rotation, but in the opposite direction. And then you apply S. So the convention that we're using here is that the rotation is anti-clockwise. So R to the minus 1 would be a clockwise rotation. So this is the equality that I will be proving shortly. And 6 follows from 5. So 6 says R to the I times S is equal to SR minus I. And in fact, we will be using the 5th part of the proposition to deduce the 6th. Let us now prove the first part of the proposition. We have here I is between 1 and n minus 1, and we want to prove that Ri is never the identity. That means R can never move a vertex to its original place. Let's see what the action of Ri does on a vertex. So the action, we know that the action of R on a vertex gives back the position of k plus 1. What about R squared? So if we apply the rotation twice, what we would get? Well, that would be R of k. So the rotation is applied on the rotation of k, which is R of k plus 1, which is k plus 2. So the number 2 appears here, and it appears here, so it is natural to say that R to the I, for some I between 0 and n minus 1 k, is equal to k plus I. So notice I here is between 0 and n minus 1 in the hypothesis. Now, let's say we take the vertex number 1, the vertex number 1 in the polygon. We want to see if Ri will move this vertex back to its original place. In other words, is Ri of 1 ever going to be equal to 1? So Ri of 1, is it ever going to be equal to 1? Is it ever going to be equal to 1 plus n? Remember that n is equivalent to 0 here, because rotating n times, it's the same as rotating 0 times. In fact, in a polygon, 0, 1, 2, 3, 4, 5, 6. So n is 6, which is the same as 0. So if we have n here, it's the same as having 0 here. So can it ever be equal to 1 plus n? And the answer is no, because I is between 0 and n minus 1. So it's either r to the 0 of 1, which is 1, r of 1, which is 2, all the way to r of n minus 1 of 1, which is just 1 plus n minus 1, which is n. And that is not equal to our desired 1 plus n. So we can never return back to the original vertex, 1. And that is the proof of the first part of the proposition. Let us now prove the second part of the proposition, which says that the reflection S is not equal to the identity, and S squared is equal to the identity. So let us prove first that the S is not equal to the identity. It means that if we choose a vertex and we show that S does not move the vertex back to itself, that means it is not the identity. Because the only way for a symmetry to be the identity, or the do-nothing symmetry, is to show that the vertices are all sent to the original places. So let's choose the vertex number 2. So let's say S of 2 and see what that gives us. Well, the formula for S is that it's n minus k, which is 2, plus 2. And minus 2 plus 2 is 0, so that all equals to n. And n can never be equal to 2 because a polygon is at least 3 sides. So now we've just proven that S does not move a vertex back to its place. So S cannot be the identity. So S cannot be equal to the identity transformation. What about S squared? Well, let's try that. S squared of any vertex k is equal to S of k. So we now use this reflection, and then we will use this reflection. So the first reflection, S of k, gives me n minus k plus 2. And when we reflect this vertex, we get n minus k plus 2, which is this vertex here, plus 2. So this is my new k, if you will. And now this is equal to n minus n plus k minus 2 plus 2. The plus 2 and the minus 2 are cancelled. The n minus n are cancelled. And all what we're left with is k. So k is transported to k. And that all makes sense. It's very natural to see that a reflection, when we are reflecting twice, we are going back to where we were. Let us now prove the third part of the proposition, which says S is not equal to Ri for all I between 0 and n minus 1. Let us use in here, in the proof of this proposition, the vertex 1. So in the vertex 1, what happens? Because the reflection is done on the axis that passes through the vertex 1, we know for a fact, like let's say we have a hexagon here, 0, 1, 2, 3, 4, and 5, and the axis of rotation, the axis of reflection, pardon me, is over here. So when we are reflecting, we have that 1 and 4 are unchanged. 1 goes to 1 and 4 goes to 4. So 1, so S of 1 is equal to 1. It does not change the vertex 1. Let's suppose by contradiction, so we will suppose something that is the opposite of what the proposition tells us, and then we will arrive at a conclusion that is absurd, that is not possible. So we will suppose that instead of S is not equal to R to the I, we will say that S is equal to R to the I. So what does that mean? That means that Ri will behave the same way as S behaves. And we just showed that S behaves in this manner. S moves 1 to 1. So this means that Ri will move 1 to 1 as well. And we have just shown that in part 1 of the proposition that Ri is never the identity symmetry. It means that it never moves a vertex to itself if I is between 1 and n minus 1. So this is impossible if I is between 1 and n minus 1. But we have just said that I is just between 1 and minus 1. That is impossible. But what if I is 0? Well, if I is 0, then r to the 0 is doing no rotations at all. But r to the 0 means doing nothing, which is the identity. So that is the identity symmetry. But that means that S is equal to R0, which is equal to the identity. And we have shown that the reflection can never be identity in part 2 over here. So that is impossible as well. So no matter what I is between 0 and n, it is between 0 and n minus 1, pardon me, it is impossible. And that is all what we need to show, because if I is n or greater than n or less than 0, that is just equivalent to going back to the same repeated rotations again and again. So only what we need to show is between 0 and n minus 1 to show that it's impossible for these i's, and that means that we can never have S is equal to R to the I. So that means S is not equal to R to the I for all I between 0 and n minus 1. Let us now prove the fourth part of the proposition. For the fourth part, we have that SR to the I is not equal to SR to the J. If I and J are not equal, I less than J, and both of them are between 0 and n minus 1 inclusive. So to see that, notice that, let's say, we will use the similar tactic as before to assume the opposite of what they're telling us and to arrive at a contradiction, something that is impossible. So let us say that we have SRI is in fact equal to SRJ. And now let us play with this equation to arrive at something that is impossible. I will be multiplying both of these sides by S, by reflection. So S times SRI is equal to S times SRJ. And that is equal to S squared Ri is equal to S squared Rj. And we have shown that already a reflection that is done twice is the identity. So S squared is 1. Ri is equal to 1 Rj. And the identity times anything does nothing on the element. So it gives only Ri is equal to Rj. So notice by hypothesis that we have this. We have that I and J are not equal. I is less than J. And both of them are between 0 and n minus 1. So this means that this statement here is impossible because we cannot have a rotation that is equal if the I and j's are not equal. If you give me a hexagon, so 6-side polygon, and you rotate 4 times, it's not the same as rotating 5 times. So this is essentially what we're saying here. This is impossible. And thereby we have proven, in fact, that this statement is impossible. So it should be not equal, thereby proving part 4 of the proposition. We will now prove part 5 of the proposition, which gives us this identity. And for this, we will prove it directly, no contradiction necessary. We will see what happens when RS is applied to a vertex. Where does it send it to? And we will see that SR to the minus 1 sends the vertex to the same position as RS. So if we apply RS, so keep things properly orderly and organized, we will say part 5, and we see that RS sends K where? Well, it sends K to see that R applies on S of K. So we will apply S of K first, and then we will apply R on the product of that. So SK sends it to N minus K plus 2 by the formula that we've known. And R of that is gonna just add 1 to whatever is inside. So N minus K plus 2 plus 1. And that is equal to N minus K plus 3. Let us see what happens when we apply SR to the minus 1 to K. So SR to the minus 1K, we will apply first R to the minus 1 on K, and then we will apply S on K and see what happens. So this equals to S of K minus 1, because when we rotate backwards, you send K to the K minus 1th position, and S of the K minus 1, we use the formula and we get N minus, instead of K, we write K minus 1 plus 2. And this equals to N minus K plus 1 plus 2, which equals to N minus K plus 3 again. So we have the same resulting position done by these two different transformations on the same K. And this applies for any K. That means that these two transformations are in fact equal. The final part of the proposition says that RIS is equal to SR to the minus I. And to prove that, we only simply need to use the part 5 of the proposition. So let us use that. In fact, we will say RS is equal to SR to the minus 1. And all what we need to do is we multiply both sides of the equation by R from the left. So R, and we write RS, and we write SR minus 1. And this gives us the R squared times S, and this gives us R SR minus 1. And now what this does is that we can say, because we have associativity in a group, we can use RS, we work with that first, and this gives us SR minus 1. So this gives us SR minus 1, R minus 1, and then we use associativity again to change the order in which we work with the elements. R minus 1, R minus 1, and by the exponent rules, that gives SR minus 2. So we just proved that R2S is equal to SR minus 2. And multiplying by R again gives us R3S is equal to SR minus 3, and so on. So essentially, it's a proof by induction. And I will leave the induction part for you as an exercise. Now that we have completed this proposition's proof, we will use these properties to come up with all the symmetries that there can be in a regular n-sided polygon. And to say that is to say how many symmetries we have, which will give us an idea of the set of symmetries. And then we will say that this set is in fact a group with the operation of composition of the symmetries. So in fact, the second proposition tells us that there are exactly, not more, not less, 2n symmetries in D2n, which is the set of symmetries. So I will be proving this by double inequality. I will be proving that there are, in fact, at most 2n symmetries, and there are at least 2n symmetries, and then that will mean that there are exactly 2n symmetries in D2n. This is a popular way of proving there are how many things that there are. So the proof starts by saying, okay, we will set M to be the cardinality of the set of symmetries. In other words, the number of symmetries of an n-sided polygon. And then the first thing we will do is to prove that M is at least 2n symmetries. Okay, so I will be producing you a list of the symmetries that there are. It is important to note that this list contains symmetries which are all distinct. In other words, there are no two symmetries that are equal. So the list of symmetries that I will get is D to N contains at least this list: the identity symmetry, the rotation squared, so rotation twice, rotation cubed, the rotation to the 4, all the way to the rotation of n-1 times. Because a rotation of n times would get me back to the same place, which would be exactly like doing nothing. So I will stop here and I will start a new set of symmetries. The first one being S, reflection. The second being SR, and I know for a fact, because of the previous proposition, that SR is not equal to any of the symmetries that are found earlier. And I can continue SR squared, and SR cubed, and SR to the 4, all the way to SR to the n-1. Why not SR to the n? It's because, again, R to the n is equal to 1. So that means now I have came up with how many? I have come up with 2n symmetries. And I've listed them here. So D2n contains for a fact at least 2n symmetries. Now let us show that they contain at most 2n symmetries. We will make use of the rigidity of a polygon. I know for a fact that if I have a square here and I have it labeled as 0, 1, 2, and 3, I can never have a symmetry which plays around with the sides too much. Okay, let me recap that, hash it out, okay? Now that I've proven there are at least 2n symmetries, I want to prove there are at most 2n symmetries. And for that, I will be making use of the rigidity of the polygon. So for example, if I had a hexagon, right, and I labeled the hexagon 0, 1, 2, 3, 4, and 5, then there can never be a symmetry that shuffles the numbers in a way which plays with how there can never be a symmetry which moves the numbers around in a way that the rigidity of the polygon is played with. So for example, if I rotate it, that's fine because I have not played around with any of the sides. However, I cannot really move 1 and 3 together. If I choose if I move 1 and 3 together, I cannot really do that, because remember, I've chosen my rotations and my reflections about this axis. So there is not really any way to get this configuration. So I will make use of this fact to say, okay, so to count the number of symmetries, note that to place a vertex K, I have 6 choices in the hexagon, or I have n choices, though. There are n choices for K. Okay? And afterwards, I will be saying that, okay, what about K plus 1 and K minus 1? Well, K plus 1 and K minus 1 have to be next to K, and they cannot be anywhere other than the places that are next to K. And how many places I have for these? I have 2. So there are 2 choices for, let's say, K plus 1. And if we choose a place for K plus 1, then K minus 1 doesn't really have a choice except the other side of K. So K minus 1 does not really count. It's what K plus 1 counts. So we have n choices to place K, and we have 2 choices to place K plus 1. So a total of the product of these 2 choices. So a total of 2 times n choices. And these choices determine completely the symmetries because of the rigidity of the vertices in the polygon. So there are at most 2n choices, and we have found all of the choices. So that means there are exactly 2n symmetries in D2n. The cardinality M is equal to 2n. Now that we have found the structure of D2n and the elements that are contained in it, we will move on to the next topic and the last one in this lecture, generators and relations. So a definition: let G be a group, let S be some subset of G, such that for all X in G, X is a product of elements in S and their inverses. So any element in G can be generated by the elements in S and their inverses. Then in this case, we call S a set of generators of G. We write G to be S with 2 brackets like that. Let us see what some examples are, which will make it clear about the definition of the set of generators of G. The first example is Z with the operation plus, so the integers. We can say that the integers are all generated by a single integer, which is 1. And the reason is because any element, let's say the element number 5, 5 can be generated by adding 1 to itself 5 times. And minus 2 can be generated by adding the additive inverse of 1 twice. So that goes for any integer in the set. That means that 1 is a generator of the set Z with the addition. What about Z12Z with the addition? What is that generated by? We can argue that it's also generated by 1. However, that is not the only option as opposed to Z plus. We can also argue it is generated by 5. Because, as you know, 1 and 5 are co-prime to 12. So if you add 5 to itself, you will never get back 0 unless you've covered all of the elements of Z12Z. And that you can try as an exercise. Try adding 5 to itself and see what elements you get, and you will see that you will get all of the elements of Z12Z. And also you will see that if you have a generator of 7, that works as well. 7 is co-prime to 12, so it generates all of the elements Z12Z. And lastly, we also have 11 as a choice of a generator. Now, if you want to see a counterexample, let's say 6. Is this a generator of Z12Z? No, because 6 plus 6 gives us back 0. And if you keep adding 6 plus 6 plus 6, that's just 6. And if we add 6 plus 6 plus 6 plus 6, that goes 0. So it's just alternating between 0 and 6. So not all the elements in Z12Z are generated by the element 6. Because 6 and 12 are not co-prime, they share a common divisor. So this is very important to determine the set of generators in a finite group like this. What about Z cross Z with the addition? Z cross Z, as some of you may know, is just the vector space of 2 dimensions, Z squared. And that could be generated by 2 vectors, which is 0, 1 and 1, 0. I am saying the word vectors, but these are just elements in the group Z cross Z. So these are 2 elements that generate all the elements in Z cross Z. You can add another set of generators, 2 vectors that form a basis for the vector space Z cross Z. And this basis will also form a set of generators as a group. So you can see there is a connection between the set of generators of a group and a basis of a vector space. What about the last example, D2N? D2N, if we look back, this is composed of these elements. And these elements are all generated by 2 elements only, R and S. You can see that from any of these 2 elements, you can generate all of the elements that are found in the list, including the identity. And I will explain that in a minute. But for now, we know that R and S will generate all of the elements in D2N. So they form a set of generators of this group. Sometimes the generators satisfy certain equations. We call them relations. So these relations are certain equations that the generators have, so certain dependencies that occur between the generators. So we write a presentation of G in this format. It makes it very clear how to describe the group G. It's much more succinct and precise to write it in this form than to write a multiplication table, which can be very tiresome and very burdensome. So G is a set of generators and a set of relations, and that constitutes the entirety of the group G. For example, D2N, we can write it as RS, the set of generators, but we also have some equations that R and S satisfy, as we have proven in the proposition. For example, R to the N is equal to 1. R to the N is equal to 1 because if you rotate N times, it's like doing nothing. That is one relation. Another relation is that S squared is equal to 1. That is another very important relation. And the last relation is that RS is equal to SR to the minus 1. And we find that these 3 relations completely and sufficiently describe the structure of the group D2N. The next example on the list is Z. And we saw that Z is generated by 1. Do we have really a set of equations for this generator? that describe 1? Not really. The only thing we have is that if we add 1 to itself multiple times, we get any element that we want in the integers. But we don't really have any type of cycle or relation in these generators. Well, being it only 1, it's really hard to find one. So we just put a line like this and we leave it blank. What about Z12Z? Well, for Z12Z, we have the generator 1, for example. We can put either 1, 5, 7, or 11, but we've chosen to put 1. And for a relation, we know that this is a cyclic group, a cycle, because we always, when we add 1, if we add 1 12 times, we go back to 0. So if we add 1 12 times, so 12 times 1 gives us back 0. Remember, this is the additive power of 1. So the additive power, we multiply the number, the exponent, by the element. So in the additive power, we have that 12th power of 1 is back to the identity element. And that is the only relation that is sufficient to describe this group. We can also say it's equal to 5 bar, with 12 times 5 being equal to 0, and that describes the same exact group. Let us move on to the next example. We have Z12Z star with multiplication, and here we can choose a generator of our set. Well, in fact, we need 2 generators. This example is a bit tricky, and I will not go deeply into it for now. I will just say that it is generated by 2 elements, 5 and 7. Because 1 element is not sufficient to generate all of the elements in the group, you really need 2, because it can either be 5, it can be 7, it can be 5 squared, 7 squared, or 5 times 7. And that will give you all of the elements of Z12Z. So it's 5 times 7, and we know for a fact some of the relations, which is 5 bar squared gives you the identity, 7 bar squared gives you the identity, and lastly 5 times 7 is equal to 7 times 5. This is important because it shows us that this group is abelian. It is commutative. The first group, Z12Z over here, I did not need to write something like that, because by the structure of the group, the cyclicity of the group, I already know that the number of times I add 1 does not really matter, the order in which I add them, so it is already commutative by nature. So it is not a simple fact to include a set of relations. It's not that trivial. You need to really think about the information that you're adding and what this information implies before adding any more information. The next example that we will talk about is this group here, which is generated by A and B and has the simple relation A squared is equal to B squared is equal to AB to the power n is equal to the identity. And in this strange looking group, we have that an element like this in the group can be simplified using the relations that are set up top. So first of all, notice that a to the 5 is basically a to the squared times a, and the a to the squared is all squared. And I write it like that because I know that a squared is equal to 1. So I want to produce that a squared somehow. And b to the 3 is equal to b times b squared. And a squared is already there, and b to the minus 1 is already there. So what do I obtain here? We know that a squared is equal to 1, and 1 squared is equal to 1, and a times 1 is equal to a. So that all is equal to a. B squared is equal to 1 as well. A squared is equal to 1. These do nothing in the product, so it's just a times B times B inverse. So B times B inverse, by definition of inverses, is equal to the identity, and A times the identity is just A. So you can see how these relations greatly simplify complicated products that look like this. If you thought that that simplification of this group was cool, let me tell you what else is cool. This strange looking group here has a lot to do with the dihedral group that we were talking about earlier. In fact, the dihedral group is nothing but an example of this group. All what you need to do is replace A by S and B by SR, and you will see what this does. So A squared gives you, by definition, S squared, which is equal to 1. B squared is equal to SR squared, which is equal to SR times SR. And now I'll be using one of the properties that I've learned about and I've proven, is that the SR in the beginning is equal to R minus 1S. And I multiplied by SR. And then I use associativity to say, well, that's equal to R minus 1, open brackets, SS, R, and SS is equal to 1. So R minus 1 identity R, and that's just equal to R minus 1 R, which is equal to 1. So we've just proven that A squared and B squared are both equal to 1, and that is consistent what we have in the relations of this group. What about A times B? A times B is equal to S times SR, and that is equal to SSR. And if I do the S's together first, I get the identity, and times R, I get back R, which is good. And now if I do it to the power n, like we've talked about earlier, that's going to be R to the n, which gives us the identity. So in fact, the dihedral group and this group are isomorphic, because all what I did was change the labeling of A and B with S and SR. This means that these two groups have the same structure, just different labeling. And for all intents and purposes, these two groups are one single group. And that is a really cool and important property that we'll be learning about. That how that different shapes that have different operations, different elements, have the same structure. It gives us a deep idea of looking at the interactions between the elements instead of the elements themselves. Thank you for watching. I'll be seeing you in the next lesson.